So this is section 9.2, polar equations and their graphs. Now, we talked last time about how to graph the difference in graphing on a rectangular grid and a polar grid. Remember that a rectangular grid, when a point is drawn, it has one and only one name. This is right 1 up 2, and so we've got right 1 up 2. On a polar graph, this point is 2 pi over 4, but it can have multiple names. In other words, another name for that point could be 2 9 pi over 4, which remember those are 2 pi apart, or I could give it the name negative 2 5 pi over 4. And negative 2 5 pi over 4 is not over here on the 5 pi over 4 axis. It's right here at the same location of P, because it means go to the 5 pi over 4 and then cross the pole to negative 2. All three of these are just names for this point P. And point Q, even though it's on the line 5 pi over 4, is a very different point. First of all, the radius is 4. The second thing is that it is in a different quadrant. But all about graphing, we can take equations that are not like anything we've seen before, and we can create them in polar format. Now, in order to do that, we're going to have a little bit of background. The first thing I want you to think about is when we were working in Algebra 2 on this equation, we had x squared plus y squared equals r squared. And that's the equation of a circle. This is the equation of a circle with its center at 0, 0, and a radius of r. And we remember this, we know that we worked with it, and it was probably also written in standard form where you had x minus h squared plus y minus k squared equals r squared, which was another circle with a radius of r, but it was centered at hk. And so if I give you this equation, x plus 3 squared plus y minus 0 squared equals 9. What is this shape going to be? It's going to be a circle with its center at negative 3, 0, and its radius is going to be 3. So what's it going to look like? Let's just kind of sketch a graph of it. We're going to go 1, 2, 3 and draw our center, and then we're going to do 3 left, 3 up, 3 right, 3 up, 3 left, and then 3 down. And we're going to draw a circle. It's not perfect, but that is basically a circle which is centered at negative 3, 0 and a radius of 3. So we have a basic idea of what our shapes look like. But now we're going to take them and we're going to put them into polar format. So let's take a basic equation. Let's take x squared plus y squared equals 9. What would we be looking at? Well, we know that we would have a circle with its center at 0, 0, and its radius would be 3. Okay? We have a circle with its radius at 3. Now, a couple things we should remember is what is x squared plus y squared equal to? R squared. And so when I convert r squared equals 9, I'm really in polar form already. But if I wanted to actually graph this in polar form on my graphing calculator, and I'm going to make a whole separate video for how to graph on the graphing calculator. If I wanted to graph in polar, I would have to set my equation as r equals 3. I would take the square root of both sides, get r by itself, and I know that r equals 3. Now I know that it could be plus or minus, but we're going to try and stay with the positive values of r for today's purposes. So notice that x squared plus y squared equals 9 is the polar graphing equation r equals 3. In other words, this is rectangular and this is polar. So I've got x squared plus y squared equals 9. I would simply graph that as centered 0, 0 with 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and I would draw a circle with a radius of 3 centered at 0. But what if I was graphing this on polar graphing paper? What if I instead was trying to put r equals 3 on polar graphing paper? Well, it's telling me the radius is 3 everywhere. So I've got a polar graph. I've got its scale is drawn so that this is 1, 2, 3, 4, and this is 1, 2, 3, 4. How come I don't have negatives? Because remember, each side is positive if you're on that side. Each side is negative when you're going across the pole. So if I wanted to plot any points for any theta value, it would simply be the circle r equals 3. So graphing in polar is really very simple. And if I wanted to graph this on a graphing calculator, like I said, I'm going to show you a whole nother video where you can put this on your graphing calculator and have the calculator draw it exactly for you. So we know that some circles are centered at 0, 0. We also knew that some circles weren't. Remember my example back here where I had centered at -3, 0 with a radius of 3? Well, let's take that equation and let's look at it from a different perspective. Let's take that equation and look at it right here. Well, this is in polar form. Let's turn it back into rectangular form. Let's take this equation and turn it back into rectangular form. I'm going to go off of this paper for a minute, and I'm going to go back to rectangular form, okay? I've got r equals 4 sine of theta. Now, in order to do this, we have to remember that x squared plus y squared equals r squared. X equals r cosine theta, and y equals r sine theta. We learned that last time. Well, I don't have r sine theta, I just have sine theta. And no, 4 is not r, it's just a number, okay? And I don't have r squared, I just have r. But what if I multiplied both sides of my equation times r? I would end up with r squared equals 4 r sine theta. Now I can replace that with x squared plus y squared equals 4 times y. Now, I know that this is another stretch. We're going to be backing up here, but we have to remember that this is not standard form. Standard form is x minus h all squared plus y minus k all squared equals r squared. I can't have any y's over here. So I'm going to move everything over. X squared plus y squared minus 4y. And I'm going to leave room, and I'll explain in a second, equals 0. Now, to be in this form, this has to be a perfect square. If you don't remember, perfect squares are found. You have x squared plus bx plus some number. If you take b and cut it in half, and you square it, that's the completing the square. And you can then write that as x plus b over 2 all squared. So this is back from Algebra 2. This is just a fast review of completing the square. Well, what is half of -4? Half of -4 is -2. So that's the b over 2. In my problem right here, my b over 2 would be -2. When you square that, you get 4. But whatever I do to one side, I'm going to do the same to the other. So I'm adding 4 to both sides. I can now rewrite this as x squared plus y minus 2 all squared equals 4. Now I'm in standard format. Now I have a circle with its center at 0, 2. Now that's going to be none to the right and 2 up, but it still has a radius of 2. So if I were going to graph this on polar graphing paper, I know that I would go to 0, 2. There's a radius of 2. So 1, 2 here, 1, 2 this direction, and 2 to the right and 2 to the left. And I'm going to draw a circle that is symmetric to the pi over 2 axis because it's a sine equation, and it's 2 above is the center, and the circle is drawn over the radius of 2. Now, wouldn't it be nice if I had a set of equations that would work for every circle? So when I start, I have r equals a. That was the first problem that we graphed, r equals 3. And remember, this was a circle. This was a circle with its center at 0, 0, and it had a radius of a. But what if the equation was r equals 2a cosine of theta, or r equals 2a sine of theta? This looks more like the last one we did, which was 4 sine of theta. Now we'll talk about that in a minute. A is not 4. 2a is the 4 value. R equals negative 2a cosine of theta, or r equals negative 2a sine of theta. So these are all going to be circles. So this is all the equations for circles. The center, however, of this problem is going to be found at A0. That's to the right A, up on the polar axis. This one is going to be at 0A. Now that means don't go sideways, so you stay on the pi over 2 axis and go up to A. This one would be found at negative A0, and this one would be found at 0, negative A. But each one of these would have a radius of A. So where would they be found? The 2 cosine of theta would be found on the right of the pole. The 2 sine of theta would be found above the pole. Negative 2 cosine of theta would be found to the left of the pole, and negative 2 sine of theta would be found below the pole. So let's take one more example of this and look at the equation y x plus 2 squared plus y squared equals 1. X plus 1 squared plus y squared equals 1. This would be a circle that is centered at negative 1, 0 with a radius of 1. But let's prove it by turning it into polar. Let's take this and multiply that out. X squared plus 2x plus 1 plus y squared equals 1. Let me combine my things I need to have together to convert to polar. I'm going to subtract 1 from both sides, and that gives me x squared plus y squared plus 2x equals 0. I know that x squared plus y squared is r squared. I know that x is 2r cosine theta, so x is r cosine theta. I know I'm trying to isolate r, so let me factor out the r from both sides. I'll divide by r because we know radius can't ever be 0. And so r plus 2 cosine of theta equals 0. I'm going to move this over. R equals negative 2 cosine of theta. This looks like this pattern right here. R equals negative 2 cosine of theta equals r equals negative 2a cosine of theta. Now what that means is that if negative 2 cosine of theta equals negative 2a cosine of theta, the cosine of thetas cancel. Negative 2 equals negative 2a. My a value is 1. Notice the radius of 1. And where would my center be located? Negative a, 0. Same center, same radius. How would we graph it? Well, it's on the cosine with a negative 2a, so we're going to go to the left, 1 space, right? We're going to go radius of 1 in all 4 directions, and I can draw my graphing coordinates, my circle, at negative 1, 0 with a radius of 1.